In this video, we will explore our fourth and final model for energy storage. We found pie charts are good for modeling energy storage, especially in closed systems. We found that energy bar and system diagrams, or LOL charts, are a good graphical energy storage and transfer model that works well for both closed and open systems. We've also used symbolic representations as shorthand for the graphical models, which also has the advantage of translating directly to an algebraic problem-solving tool. Now we're going to learn about a model for energy storage that takes into account the passage of time and changing energy storage modes. This model is known as the energy time graph, and it's not a very difficult concept to understand. We'll step through it carefully enough that I think you can get the basic idea pretty quickly. Imagine this situation where a skateboarder is going back and forth on a half pipe. We'll use this as an example to both review the models we already know about and also build on it to learn about the energy time graphs, which are today's topic. You can see from the fact that she returns to the same height every cycle back and forth that this is a model that has such little friction that it can be ignored. This will make for a simple set of models, and what we'll learn here could be modified by adding some thermal energy if friction were to be accounted for. As we use this example, we'll be assuming a closed system that includes both the skater, including her skateboard, and the Earth. Let's model energy storage as it changes over three positions. A will be at the top left of the half pipe, B will be at the very bottom, and C will be up on the right-hand side at the top. First, let's change from position A to position B using a pie chart to represent the energy storage. At A, all the energy is stored as gravitational, and at B, it's all stored as kinetic, as the gravitational has dropped to zero. Next, we'll use an LOL chart to represent the same situation. We'll see that all the energy is stored as gravitational at A, so there's a large bar on EG, and then at B, the same size bar appears as on EK because this is now kinetic energy. Size of the two bars is the same. There's no losses or energy gains in the system circle because it's a closed system. Translating this to symbolic representation, we find that all the energy stored at A was gravitational, and that's equal to all the energy stored at B, which is kinetic, so Eg at A equals Ek at B is the equation that models energy here. Now let's get into the next energy storage model. In an energy time graph, energy is on the vertical axis and time is the horizontal axis. In this system, gravitational energy starts out high while kinetic energy is at zero. As we go through time from A to B, gravitational energy drops to zero while kinetic energy rises to the same level that gravitational energy had at A. In other words, energy is switching gradually, and by the time you get to B, all of it is stored as Ek and none of it is stored as Eg. Now let's go through the same process as we change from B to C on the half pipe. On the pie chart, we see that the energy storage is all kinetic at B, then it's all gravitational at C. On the LOL chart, you basically see the same thing. From Ek to Eg, the bars are the same height, and there's no energy input or output in the system circle. Its symbolic representation clearly shows that all the energy is stored as kinetic at B, and that's equal to all the energy which is stored as gravitational at C. As we explore the energy versus time graph, we'll leave the time from A to B on our graph and continue on from B to C. As we've seen with the pie chart and the LOL chart, the energy stored in the gravitational mode rises from zero to the maximum amount as we go from B to C. At the same time, the energy stored as kinetic drops from the maximum down to zero. Now, evaluating what's happening when we go from C back to B and then ultimately back to A will tell us a familiar story, but in reverse. So here we go from C to B, it's all gravitational, and then at B it's all kinetic. As the skater drops to the low position and speeds up, LOL chart, same story, no inputs or outputs, so the bars are the same height, and at first it's all G, and at the end it's all K. The energy symbolic representation shows that the amounts of energy are equal, but they're just stored in different modes from C to B. Now when we get to the energy versus time model, we can see that there's a repeating pattern here. It's going to repeat itself. The energy storage mode just continually switches back and forth between gravitational and kinetic as time goes on. One more step, let's go from B back to A. Pie chart is going to show us going from fully kinetic to fully gravitational. And so will the LOL chart. And the symbolic representation will tell the same story. And when we get to the energy time model, clearly we can see that if we were to add more cycles from A to B to C and back to B and then back to A again, we would see over and over again the same repeating pattern where gravitational drops to zero at the same time as kinetic rises from zero, and then it would repeat over and over again. Not all energy and time graphs are this predictable, but in a closed system, energy is constantly being transformed from one mode to another, and so there are often times when one energy storage mode drops simultaneously to another energy storage mode rising. The total amount of energy will just be the sum of all the gravitational and all the kinetic at any given time, and that turns out to be a constant number, not surprisingly, since this is a closed system. If we were dealing with an open system, for example, let's say that the track was outside the system and we were accounting for friction, the total energy in the system would be dropping, and so that means that these peaks where Eg and Ek are rising to their maximums would just be a little lower each time. We'd still have this cycling back and forth between gravitational and kinetic, but instead of the total energy being a horizontal line, it would now dip closer to zero as time goes on. It would have a negative slope, and those peaks would rise up to meet that changing total energy line. Hopefully, this gives you an idea of how you can use an energy time graph to model energy as time goes on. As you're trying to do examples of this, always be thinking about different distinct times during an energy change event, and think about what would be the value of each of the energy storage modes that you'd be tracking. As always in our study in this unit, this is approximate and it's not quantitative. In other words, we have no numbers or measurements, so don't worry about the actual sizes of any of these values. Our only objective here is to just get the main idea of how to model energy storage and transfer in our physics practice.